For this first question involving the photoelectric effect, we're given a graph that's a little bit different from the one that we saw in class. Now that's okay. They're still looking to see that you can work with something that's a little bit unfamiliar to you and make some sense of that. So on this graph we have the kinetic energy that these photoelectrons are going to have. That's on the y-axis, and that's in electron volts. And then we're comparing that on the x-axis to the frequency of light that causes those photoelectrons to flow. Now the photoelectrons, they only exist if the photon is high enough energy, high enough frequency, or low enough wavelength to eject it from the surface. And so as soon as it ejects from the surface, if it just barely moves from the surface, we would say it has zero kinetic energy. And as we give it more and more energy, so higher energy photons causing it to move, it's going to have more and more kinetic energy. Now we really can't have negative values for the kinetic energy of these photoelectrons. But it is useful to think about extending this line backward. If we extend it backward a little bit, we can see, it looks like I didn't draw that very well. Let me try that again. Something like that. If we extend it backward a little bit, we can see that it would cross the y-axis. That's a little better. It would cross the y-axis at this point here at some negative value for kinetic energy. Well, if we think about what the meaning for this would be, again, physical meaning here, negative kinetic energy just doesn't make any sense. So if it has negative kinetic energy, well, that we could say more that would be the amount of kinetic energy we would have to give it just to have it at rest on the surface, free instead of bound with the rest of the material. So if we had light striking at 2 times 10 to the 14th hertz, then that electron would, well, it would climb to a higher energy level, but it would still have this negative value for kinetic energy, negative 0.5 electron volts, it looks like there. And so we'd still need to give it another positive 0.5 electron volts just to get it to be completely free of the material that it's bound to. If we go all the way back here and the light that we shine has zero frequency, which just means we don't shine any light at all on this, and we get to this position a little less than -1, and the one that's closest to that is negative 1.5 electron volts. My drawing doesn't quite show that, but close anyway. Negative 1.5 electron volts, that's how much energy we would need to give this if we didn't shine any light on it yet. So if there's no light shining on it, it needs another 1.5 electron volts of energy just to be free of the material that it's a part of, at rest on the surface. That's the definition for the work function. So the work function is just going to be whatever we get for the y-intercept here. And the y-intercept, it looks like, is supposed to be at negative 1.5 electron volts. So on this one, A would be the correct choice. In general, on these graphs, even if it's a little different value here, we looked at stopping potential yesterday instead of kinetic energy. But in general, on these, when you want to know about work function, you're going to be looking at the y-intercept for that. If we're looking for threshold voltage, we'd be looking at the x-intercept for that. So the threshold voltage here would be a little less than 4 times 10 to the 14th hertz. Now on these ones, we're going to keep in mind the way that the photoelectric effect works is these individual photons, these particles of light, are striking individual electrons. And if there's more photons, they can strike more electrons, but that's not going to have an impact on how fast each electron moves. Each electron only gets hit by one photon. So the only thing that influences how fast that electron moves or how much kinetic energy it has is going to be the energy of that photon that hits it, which is directly proportional to frequency. We can write this out in an equation. We say K max is equal to HF minus phi, where phi is that work function, h is the Planck's constant, and f is the frequency. So the maximum kinetic energy, K, of these photoelectrons relative to the frequency of the light for number 15, that's a linear relationship. And the slope of that line would just be h, which is some positive number. So as frequency increases, we should see K increase at a constant rate. The only one that shows that is A. And then for 16, the kinetic energy as a function of the intensity of incident light. Well, intensity is like brightness of the light. With the particle model of light, intensity is just equivalent to the number of photons. So if there are more photons, that looks like a brighter light to us. And if there are fewer photons, that'd be a dimmer light. Each individual photon has some amount of energy equal to h times f. There's no term in here for amplitude or for brightness. So the only way that we can increase the energy in terms of brightness for amplitude is to have more of these photons that each have an energy of hf. So if we have more photons, what's that going to do to the maximum kinetic energy? Well, nothing. All we care about is the frequency of each individual photon. So if we just keep that the same, all we're doing is adding more photons like that, then the kinetic energy of these photoelectrons won't change. We'll get more photoelectrons, but they'll each have the same, or they'll all have the same maximum kinetic energy. So on this one, as the intensity changes, K is constant. That's what this graph is showing. K doesn't change as our x value does change. So on this one, E is the way to go.